Basically, you have a sample chamber that you keep in it. You can have a sample robot, but typically graduate students are the robots. They can do the work. But if there are so many samples, there are systems where you can place 50, 60 samples at the same time in small sample holders like this. You put that in, you tell it to, and it's all in an inert nitrogen environment so that there's no carbonation. You tell the instrument to go from whatever is the ambient temperature to say 1000 degrees Celsius at the rate of 10 or 15 degrees Celsius per minute. It keeps on ramping the temperature. As it keeps on ramping the temperature, it keeps on measuring how much of mass is being lost because the gases go out. And you get a picture that's like this, the purple line. So that's a mass, starts at 100 total mass, and after some time, when you get to 1000 degrees Celsius, you have about 83% weight. So you lost 17% of the mass, of the initial mass. Now you know that you have, here is still about 100. So you can say that until about, and then you can take the first derivative of that curve. That's the differential thermogravimetric curve. That's the first derivative, which makes the determination easy. So I can say here about 150 degrees Celsius, I see a peak, and I look at the literature and say, 150 is typically ettringite. So that is the ettringite peak. Calcium hydroxide, CSH, there's a little confusion on how much CSH, what's the temperature of CSH decomposition based on what is the C over S ratio, and all those things. But you can still get a feel for what that value is. Portlandite, calcium hydroxide, never a problem. If you see anything between about 450 and 500 degrees Celsius, that is calcium hydroxide in the cement system. Look at how lovely that derivative peak is, and you see how lovely that mass drop is. That is calcium hydroxide for sure. Calcium carbonate, depending on the polymorph of calcium carbonate, depending on what form of calcium carbonate, vaterite, aragonite, depending on what form of it, you may see some slight differences, but anywhere between 700 to 850, you can be sure that's calcium carbonate calcite. So you get all these identifications, and then based on how much of mass is lost in Portlandite, so you start from here about what, 89 all the way to about 86. So 3% is lost. And then you look at water stoichiometry, find out how much of calcium carbonate is there, calcium hydroxide is there in the entire paste. So another example of here is a plain paste, some different aluminosilicate added, 6%, 9%, 15%. You see how the total mass changes, which means also you can do between 105 and 1000, the total mass loss divided by 0.23 will also give you the degree of hydration. Right? So you can do so many things with TG. Limitations, different phases with weight loss the same temperature range. Monosulfates and CSH sometimes have weight loss the same range. So we typically say CSH, no, we typically say calcium hydroxide, calcite, and then all the remaining amorphous compounds. So exact CSH sometimes hard to determine. Water loss influenced by different hydrates, sensitive to drying conditions, so you have to look at all of that. You can do differential thermal analysis that measures the difference in temperature, differential scanning calorimetry that relies on difference in energy. So these are a little more advanced techniques, DTA and DSC. Thankfully, these equipments have become less expensive now. They used to be very expensive, but with advances in electronics and instrumentation, these have become less expensive. So in the US, I can get a very good TGA that does a lot of different things for about $30,000. So $30,000 is roughly what, 20 lakhs in Indian rupees at this time. The problem is the Indian guy who supplies this will tell you 40 lakhs. And that is the difference that you have in India. So I was working with IIT Madras and looking at different types of equipment for a rheometer, for example. A rheometer that I can get for say $50,000, $60,000, all with all bells and whistles like a Benz car. So $60,000 is what, about 40 lakhs. They were talking about 75 lakhs here. So sometimes you have some of these instruments are very expensive, but On the other side, there are a lot of people manufacturing very similarly these things in India and China. China, I wouldn't say I would trust, because I actually bought a Chinese instrument because it looked very, I bought a particle size analyzer. In the US, a typical good particle size analyzer will cost me $25,000. I looked online and saw these wonderful reviews of a Chinese particle size analyzer for $7,000, right? The typical Indian mind got up and said, yeah, great, I should buy the cheaper thing. And then I talked to those guys and they said, yeah, we do this and all of that. And then they had to send it to me, and shipping in Los Angeles, I had to pay some customs money. It came in, all of that. Nice particle size analyzer, nice laser, all of that is good. But I have to tell the particle size analyzer what my D50 is to give me a distribution. Because the software is so crappy that it has nothing inbuilt in it, or whatever D50 I give it, it will give me some kind of a statistical distribution. So basically, I can put a powder, the laser will do the analysis, but I have no way to get it out. And because it is this company's instrument, who will write another software for them? So basically, it's now sitting in my lab as an expensive paperweight. That's what it is. So sometimes be very careful. The things will look very good, very shiny, very polished, but it may not do the work. There are some companies in India that have started producing many of these things, subsidiaries of these companies in India, some people who have developed it on their own. But if any of you are mechanically oriented, you have some money to start these things up, this is wonderful business, okay? The technology is out there. None of these, well, there are some patented things that these many companies do, but the fundamental physics has no patents. You can look at the fundamental physics and you can probably get, I mean, if you have a very good machine shop that can machine things to very good fineness, you have a good guy who can put together these things in terms of systems and samples, you have a good marketing person, you can get a lot of money. You actually can do, and if you can do this marketing well, you can get these things made in India itself. I don't know why. It's also a monopoly of all these Western companies which they sell for. And all these companies, if you look at, they have huge market in India. Lot of engineering colleges, lot of universities, lot of research labs. And suddenly anybody who I talk to in the US, they said, oh, I was in, so you know, if some of the general manager of these companies come to my lab, they want to say, oh, professor, I was in India last week. I said, what are you doing in India? Oh, we are selling these things like a hot cake in India now. And they're selling this to all these universities and at such a premium that if I ask him, so I do this all the time. They say $40,000 startup, I say I'll take it if it's 25. I'll do the street side bargaining stuff for all these instruments, and I do, and I get that also. They said, oh no, it's very expensive. I said, no, if not you, hey, there are always other suppliers, there are other manufacturers, I'll go with them. Because I know what is happening inside the system, you don't have to come and teach me yours is the only thing, and go somewhere else. And they typically give you for what you ask for. Because they're making all this money in India, so they can afford to give me for cheap. Pretty much everything in my lab I bargain, and now because I'm so successful in bargaining, other professors when they buy stuff, they ask me to bargain. Hey. So you know because typically people in the US, they're not used to doing this, right? They don't know. We are so used to doing it. My uncle, I was with him in Delhi when I was young. The guy in the roadside, so you buy this handicrafts, artifacts, things in Delhi on the roadside. That guy will say 100 rupiah. He'll say 20 ko denge kya? So he'll say no. So okay, we'll walk off. And he'll call, sir, 40. Right? It's exactly the same argument. But we're talking larger numbers. But you know, he'll give me, and I bought an AFM recently, atomic force microscope, $100,000 he quoted. With all bells and whistles. I said, I'll give you 40,000 right now. We have a deal. I'll write a check for you today if you are giving it me for 40,000. So we are taking a big loss. I said, yeah, don't sell anything in loss, please. Your company, please don't lose it. 2 days back, he's coming and saying, Professor, can you make it 50,000? I said, 45. And he gave it immediately. $100,000, I bought it for $45,000. And you should do that also. So if you are in colleges here, when some foreign instrument guy comes and sells it and says 70 lakhs, say 50 lakhs, I'll take it today. Typically they'll say, no, we are losing it. But then you create, this is how you should do a lot of marketing also. You should say that, no, I know that you gave this in such and such place. You can bluff also sometimes. I heard that you gave it to IIT at so much of price. Oh, really? Or your competitor gave it to IIT at such a low price. They want business, right? They all want business. They'll do it. So try to get good instruments try to train your students well in the instruments. Try to know, like I keep saying, pitfalls. The drawbacks that you find you may have, that's what you should look at. Because the other parts are very straightforward. TGA, DSC. So DTA and DSC gives you the rate of energy flow. Thermogravimetric analysis was just mass, right? We never talked about energy. But mass and energy are related. So you can look at energy flow DTG. Again, you see those temperature differences. What will this peak be? What will this peak correspond to? Calcium hydroxide. So you will see very similar results, just the interpretations are going to be different, and for certain things you have to have that. And I'll do this, another sophisticated method. I don't know how many of you have access to it. It's probably very hard. This is very similar to an MRI. MRI at a very small scale. But most institutes with a lot of physics research will have it. Physicists use this all the time. Nuclear magnetic resonance. The idea that nuclei of atoms spins. Okay? So nuclei of many atoms spin, and then so if you apply a magnetic field, the nucleus can line up or against the magnetic field. The idea that if I apply a small magnetic field to a nucleus, the nucleus can line up along the magnetic field, or the nucleus can line against the magnetic field. So a spinning proton, for example, creates a magnetic field. Proton is what you have in the nucleus, right? Protons creates a magnetic field. With no external magnetic field, you have all the spin directions differently. But when I apply a magnetic field of B, you see all of them aligning in the direction of the magnetic field here, right? So the nuclear magnets are oriented with or against the direction of the magnetic field. That's what you're looking at. Very complicated instrument with a lot of things that you have. We have at my university, we have the basement of one building full of NMRs. I think we have 10 or 12 NMRs in that building itself. And you have to have it in the basement because you have to isolate vibrations. When the nucleus is spinning and you're trying to find out how much is the nucleus spinning, you can't have a car driving through, or you can't have people knocking doors or doing it. So you have to have the whole building completely vibration isolated. So that becomes very expensive. So you have a lower energy state. A nucleus is in resonance when it absorbs radio frequency energy and spin flips to a higher energy state. So it absorbs this delta E energy and spin flip. You see here? Spin direction. Look at the spin direction. At the lower energy level, this is spin direction. At a higher energy level, it spin flips. So basically what you're doing is trying to find out what is the spin flip in your nucleus when you apply different levels of energy. The advantage is that, I didn't do more pictures, but I'll tell you quickly what you will get if you have an NMR spectrum. So you can do 27 SI NMR, right? Silicon atom with an atomic weight of 27. Now, I'm doing 27 SI NMR. What am I going to find out? Because I'm spinning the nuclei of what in 27 SI? Of silica, right? What do I have with silica in the system that I'm looking at? If it's a cement paste, what do I have? That contains a lot of silica. What do I have? CSH. CSH is the only thing that has silica. Now, what you will have in CSH? Do you think CSH is a very homogeneous thing? No. CSH is very, very heterogeneous. The silica tetrahedron, remember the Si4 tetrahedrons, right? The reason why, now, is your CSH in cement paste two-dimensional or three-dimensional? I showed you the model, Feldman-Sereda model for CSH. How did it look? Did you see 3D in that? Layered, right? Any layered structure is a 2D structure. You have a mat on the floor. Is a mat 2D or 3D? 2D, it's a layered structure. So CSH is a 2D structure. In a 2D structure, you have a lot of quartz, right? Quartz will be called, or silica, will be coordinated with a lot of different things, right? Silica will be coordinated with alumina. So based on the coordination of silica with different things, you call different silica structures like Q1, Q2, Q3, Q4. It's the coordination levels of silica. So you find out through NMR how much of each of these coordinated silica are there. So for anybody who is doing geopolymers, anybody who is doing fly ash geopolymer, all you get is Q4 silica. Why? Because the silica in the fly ash does not change its state. All it's doing is replacing some silica with alumina and some sodium, right? So it'll all be Q4, the natural state of silica will be there. If you're doing normal CSH, you will have a lot of Q2 and Q3 silica, very little Q4 silica, because your actual silica structure will be completely decimated. And that's why from 3D you're going to 2D. Your actual silica structure will be completely broken down because of the abundance of calcium ions. Okay? So you can know from that what is the actual structure at an atomic level. So think of it, you look at SEM at a meso scale, you can look at further smaller magnifications. That's morphology, that's what you have. XRD will give you crystal level information, just the crystalline position locations. Thermogravimetry will give you the amount of these materials formed. NMR will give you at an even lower level how are individual silica atoms positioned in this, right? So, if you are a concrete engineer, do you think you need NMR? Forget it, right? Don't need it. If you're doing research, if you're developing a new material, you want to really understand what's going on underneath. If somebody tells you, I want you to prove that this is the state of silica in a structure, then you need it. But for general purpose, I wouldn't recommend it. It's extremely expensive. So I did not know anything about NMR until about 5 years ago. So I went to a professor of physics who was about to retire at Arizona State, very old man, 75 years old, who built his own NMR 25 years ago. The sophisticated thing that this company is built, he built his own thing. So I went and told him that I want to learn NMR. He said, yeah, perfect, I'll teach you. And he asked me first question, do you know quantum mechanics? I said, no clue. I know I have seen Schrodinger's equation. That's pretty much what I know about quantum mechanics. So he said, here is a book. Here is my notes that I teach the advanced quantum mechanics class. Look at it and come back. I looked at it. It was Greek and Latin. I couldn't understand a single thing. I couldn't go beyond page 5 or page 10. So I went and told him, sorry, this is too much. I'm a civil engineer. I need things simplified. Because I don't know enough physics to understand what's going on. So he said, it'll be a losing cause to me also to teach you physics. Forget it, I'll teach you the operation of the machine. Yeah, I can learn that. You show me how things work and show me how to put sample in, show me how to interpret, I can do that. So it took me about 3-4 months working with him and a lot of hours to understand how to get the results and how to interpret the data. But the advantage is you get hands-on experience. And if I see an NMR spectra, when somebody publishes, I review, I understand what that actually means and what they were trying to do. But real life, is there any use in the type of materials that I'm studying? No, I did it for some geopolymers. We want to find out what the exact structure is. We did a few things, but I don't do it every day. I mean, I don't have need to do it every day. When somebody tells me that I need this concrete for this purpose, when I tell him, yeah, I'll do NMR, they'll say, get out of here. That's not what we want. So again, like I said, every tool has its place. You don't use a machine gun to kill a fly. You use a SWAT bat to kill a fly. You use that thing that's available in India. So one of my friends from the US came to India. So I took him to Kerala, our house. We took him to all places in Kerala, elephant safari and things like that. So he came to our house and he stayed with us. Evenings, rainy season, mosquitoes. So we have this mosquito bat. He was so surprised to see this. You don't see that in Western countries at all. This lovely bat, you press a button and you see this spark going on and the mosquitoes dying. Right? You don't see that there. So there's a tool for everything. I mean, if for India you need it, you improvise it, you create this right tool. You did not create, if it's in the US, they would have created something else for that. But there's a tool for everything. Make sure that you know how to use the right tool. And just because you have a tool, you don't use it. Right? Just because I have this big bulldozer, I don't drive it to go to Bangalore, right? I can drive it to Bangalore actually. It drives. But would I do it? No. I'll use some other way of transport. use the right tool, that will give you the right results. Okay, SEM, I thought I'll show you some more of SEM. Want a break now? 11? Oh, it's okay, 11:30. Okay, so I would need, I know how many slides more do I have? You guys are not bored, right? So I have about 100 more slides in this. So I'm not going to finish it today for sure. So this will slip on for one more or 90 more slides. This will slip on for one more session. But if you're bored, let me know. Because I don't want you to be sitting here for 5 days as a torture. Okay, that's the last thing I want. Because, see, I tell this to my students all the time. I get energy from you, right? This is like you see some politicians never stopping. That's because the crowd is chanting. It's like I get my energy from you. So if you are bored, let me know so that we can take a break, we can relax and then get back, because there's no point in preaching to a very tired crowd. So anytime you're tired, let me know, I'll stop and we can have some discussion. Anytime you think you need more discussions on a topic, let me know. Because in 5 days, it is impossible to teach anybody everything about concrete. But in 5 days, we can actually make a good start. That's all I want. In 5 days, I can kindle your curiosity. I can make you two things. I can either make you more excited in concrete, or I can kill your interest in concrete. Either way, either way is good. Because now you will partly decide, should I work on concrete, should I do it? Maybe after this class you say, no, this is not for me, I'm moving on. I helped you make a right choice. Right? Or you might think, this is wonderful, I want to work on concrete, I help you make another right choice. So either way I win. Okay? So the idea is to make sure that you get what you want, you get the information to learn. So anything in engineering